Cool. So my name is Evan. I'm from Oyala. I'm sorry I need to give this 30-second pitch. We are also hiring. Most of our backend big data stuff is in Scala. We also have an old Rails stack, but we definitely, we have multiple teams using Scala. So also, if you're interested in doing really cool, both real-time and a lot of big data systems, working with Spark, Cassandra, and other really interesting technologies, feel free to see me. So, Akka. There is a really big term now called reactive programming. You might have seen that Coursera has a course called Reactive Programming. I actually tried to take the first few weeks of that, but got too busy. What is reactive programming? So, and that's a lot of what underlies Akka. Reactive programming has to do with writing event-driven, scalable, and fault-tolerant applications. And reactive in the sense that the real world has a lot of events going on, and you want to react to them in a sensible way. And a lot of the components you might have heard about in the Scala stack, especially the type-safe stack, solves these problems. So we have Akka. We have Play, which is based on Akka. Play is probably the most popular framework. Who here has not heard of Akka? No one. And just out of curiosity, how many people are using Akka at their companies? Awesome. How many people are using Play? Yeah, so if you use Play, you're probably also very familiar with Akka because Play is completely based on Akka underneath. So we're going to talk about reactive programming with Akka, and specifically about how we use Akka and Scala at Oyala, and some of our stories with productionizing such systems, and how we can really make how we can productionize them effectively. And I'll talk about a technique called Stackable Trades that we use with our Akka actors to instrument them. Just a brief overview of Oyala. I'm sorry about this projector. We are about 5-6 years old. And we basically are like, you can think of us as like a YouTube for business. So a lot of our biggest customers are the likes of ESPN, Pac-12 Networks, Victoria's Secret, REI, people that like to serve a lot of videos on their site. And everyone who watches videos on their sites ends up with events through us. So we process a lot of data, over 2 billion pings a day. How did we get started using Scala? Well, we were actually mostly a Ruby company. Even MapReduce jobs were written in Ruby. And what we discovered was that that was before I went there, right? And now what we discovered was that Ruby is a good language for a lot of things, but it is not a really good language for doing big data stuff. It is slow, and it doesn't integrate natively with Hadoop. We're not able to take advantage of a lot of input formats and things like that. So we started experimenting with Scala for doing real-time analytics, for which we were pretty sure that Ruby wouldn't work, as well as for MapReduce pipelines. And what we realized was that we could get about a 1 to 2 order magnitude in performance boost just from switching to Scala. So we were pretty happy with that. Made a lot of sense for us. So now we write 100% we have actually banned Ruby MapReduce jobs. Or at least we've banned writing new ones. Unfortunately, we still have some old ones running. And we use Scala and Akka with Storm, with Spark, with MR, with Cassandra. Basically, all of our big data stuff is written in Scala. So I want to talk about the problem of ingesting 2 billion events a day a little bit. You have a video player. This feeds into a front end of, say, Nginx servers. We feed them, say, into Kafka, and then we feed them into other pipelines. What is an effective way of processing all this data, right? And we'll start with a couple places where we use Akka. The first place is a place, that reads live.logst. We have a daemon called live.logst. And what this does is it is designed to get new log files, which have been written by Nginx, and forward them on to Kafka. And this was kind of like one of our first forays is a production system using Akka. It's very simple. It's simply tailing log files. It picks up, basically what we do is we have one actor reading each file. And actors, the good thing, you don't really worry about threads or how like logs or anything like that. This is pure message passing. So one actor is reading log lines from a file. It processes them a little bit. Then it passes them on to another actor, which forwards them to Kafka. So it's pretty good use case for Akka because it's completely event-driven. As you're reading files, you get new files, that's another event. Or rather, when you detect a new file, we create a new actor. Actors are very cheap to spin up. So it can handle many thousands of log lines and allow us to do some coordination on top of that. So that was our first foray. That works pretty well. We still have it in production. The second system where we started to introduce Akka is funny enough in Storm.
Sorry for being ignorant, but what is Kafka doing?
Oh, sorry. So Kafka is feeding the logs onto other processing systems. Where we do a lot of our analytics for I guess to back up. What kind of analytics we need is that someone like ESPN wants to know where are people watching video? What kind of devices are they watching? They want to like slice and dice their data. So after stuff goes through Kafka, then that's where we do all this processing with like Spark and Storm and other kinds of frameworks.
Can you just describe what Kafka is for many folks do not know what it is?
OK, thanks. So for those of you that don't know, Apache Kafka is a message queue, and it's kind of like RabbitMQ. It's used for very high volume message handling. Yeah.
Are you using any kind of a front-end web server, or are you just Nginx is just taking this traffic and then flushing it to a log? You're saying
Nginx is taking the traffic and flushing to a log. Yeah. So Nginx is our front end.
Are all the parameters in these requests put into URL, or where are they?
Yeah, everything basically Nginx. Yeah, everything is encapsulated in HTTP REST kind of. In requests. Yep. So after Kafka, we started getting into real-time analytics. So we started building a. This is really cool. You can get the number of people actively watching videos in just a matter of seconds, and we did this. At that time, Storm had just been released, so we started writing this in Storm. I'm actually the author of the Scala DSL for Storm. So Storm is neat. How many people have not heard of Storm, by the way? OK, so for those of you that are not that don't know, Storm is a real-time distributed processing system. It's used for stream processing. You're getting a lot of events in, and you write. They call them spouts and bolts. You can picture like a water flow system where like spouts are the source of the data. And I'm not sure where bolts comes from, but basically that's kind of like the processing for the data. And the way that it works is that you define parallelism. So bolts are the processing unit, and you can have multiple of them. They are distributed across machines, and they do some work. Strictly speaking, Storm actually doesn't have anything to do with Akka. You could, and most people will not use Storm like actually with Akka. So forgive me if this is a slightly like advanced topic, but we use. So you can think of like bolts will send message to each other. It's kind of like actors, but it's more of a like a Java-ish API. But what happens is that these run on one machine. So when something fails and one machine goes down, the whole boat, one boat might go down and then come back up. For us, though, we wanted more granularity than just one machine. We wanted to have some concurrency within a boat. So we used actors within Storm for that. And the reason why we do that is because you don't really need them. However, the good property is that there are some things that you want to process together where, like, if it fails, you want to bring them up together. And it might be more complicated to treat a system where you have A and B, and one fails, but the other doesn't fail. And so when you come up, you have to take care of a lot more cases. For us, it was a case that these two guys did work that happened together, so it was easier for them to fail together and to come up together. I can explain a bit more. But basically what we learned from Storm, we found that Storm was too complex to use in production. The reason is because inevitably what happens is that you deploy a system to production, then you have people on call. At 2 a.m., the phone rings or you get a page. And Storm has a lot of moving parts. It has supervisors on each machine. Then it has Zookeeper. It has a central managing agent called Nimbus. This is all good, but we found that it was pretty hard to figure out exactly where the problem was. You have a lot of logs all over the place. So it was fairly complex. After this, we iterated some more. How many people have heard of Aqua Cluster? A few people. So starting in version 2.1, I believe, Aqua released a clustering layer. And this is pretty cool. What Aqua Cluster is, it's a peer-to-peer. It's kind of like Cassandra, if you guys know Cassandra or Amazon Dynamo. It's a system where there's no central master. But if you have n nodes and they all belong to Aqua Cluster, they will know about each other and message each other and know when one of the nodes dies through peer-to-peer gossip. It's extremely cool technology. We thought we would try this out. So we were going to replace our Storm processing with an Aqua Cluster-based pipeline. And the way that this works, this is distributed, is that you have a Kafka consumer. This pulls messages from the Kafka message queue. And what this does is this will forward to everything in red is an HTTP service. So we're trying to create an ingestion service as a REST service. And we use Spray because Spray at that time Spray had the best Akka support out of all of the Scala HTTP libraries. The next part is really neat. We have something called a cluster router. And what the cluster router does is it's an Akka. So sorry if I'm throwing a lot of terminology out. In Akka, you have a lot of actors. And a lot of times, a very common pattern is that you want n actors to do work for you. They might be on the same node. They might be distributed. So the way that you spread work out to these actors is through something called a router. And there's different kind of routers. There's ones that do round robin. There's ones that send them the random messages. There's a lot of different types. So one type is called a cluster router. And that is aware of different nodes in a cluster. So if I send a message here, it is able to spread out its work across the cluster. And in our case, we did some partitioning. So each of these processing actors is responsible for a certain shard of messages. So the cluster router allowed us to redirect and do consistent hashing, such that messages that belong to the same shard always end up in the same place. So
You sharded for because it needed to be that handler, or you just wanted to spread the load?
we actually wanted a particular kind of sharding. So it wasn't just for spreading load. Yeah. There was some state encoding going on. So this was good, but it was still too complex. We had, there's a lot of nodes talking to each other. The Aqua Cluster in 2.1 wasn't quite ready. It was still kind of an experimental phase. Since then, it's actually been it's no longer experimental. So now it's a lot more stable, and there are actually a lot of people using it. One thing we found was that, so Scala is a dangerous language. Akka as a library, there's a lot of different concepts you can use. There are actors, and there are futures. So just out of curiosity, how many people don't know what the difference between actors and futures are, or is not quite aware? So so I won't go over that. So one thing is that HTTP requests are a request and response model, but actors are more of a message passing. The actors say, let me tell another actor something. Futures say, let me go and do some work and come back with an answer. So the natural intuition you have is that for HTTP, which is request response, you want to use futures because you want to send out some work, you get a reply back, then you can send back the HTTP response. So that's a pretty natural pattern. So what you end up doing is you start mixing actors and futures. I might have an HTTP endpoint. This will fire off a future to an actor to do some work. Then when that actor is done, comes back with an answer, then we would respond through the HTTP response. This is fine, but we found out that when you had a lot of actors and futures mixed together, it still became hard to understand. It was hard for engineers to conceptually wrap around when things transitioned, and it was hard to keep track of both. In the end, what we found was that using mostly actors was a lot easier for most people to understand. We had very few trouble. Like most people got the idea of actors right away. Maybe because it's almost like pure small talk, like object passing with message passing. And futures were much harder for people to understand for whatever reason. So the final system that we moved to is a pure actor system where you have independent nodes. And we basically used Kafka to partition our messages. So Kafka has a really nice property that Kafka has what are called topics. And so let's say that I'm ingesting a Twitter feed, and that would be one topic. And maybe my Facebook stream would be another topic. And within each topic, you can then set a number of partitions. And when I'm sending messages into Kafka, I can actually I can essentially shard my messages in Kafka and push to particular partitions based on hashing. So we decided to partition in Kafka, which means that each of our processing nodes is now completely independent. And we are just reading from Kafka, pushing to one actor, pushing to another actor, pushing to another actor. It is super simple. It is completely linear. It is really easy to understand. So that's a system that we are very happy with because it's very simple to debug at 2 a.m. in the morning. There's only one application and only one log file. Yeah. Question? Yeah, that's a really interesting topic. So we only do a kind of we've thought about this problem. There are actually some frameworks on top of Akka that provide the message guarantees. I think it's built into the new version of Akka now. At the time, they didn't have that. And our plan was actually to we don't do so much the message delivery guarantee at this level. It's more of a system-wide level. Basically, these guys write to Cassandra. So we do a check. We check the data based on statistics here, and we loop it back. So basically, we do guaranteed message delivery, but it's based on a whole system. It's wider than just the scope of this thing. It's how we do it. But there are definitely advantages to doing guaranteed delivery within this system itself. You get much faster response times. And yeah, I think the common way is that if you detect a failure, you keep track of the. So Kafka is different from most message queues in that the way it works is that you read off of offsets into a file. So the typical way to do guaranteed message delivery is that you keep track of the latest offset that has succeeded. So I have an offset here, it commits here, and if any failure happens, I roll back to the latest commit and I replay messages. That's typically how the pattern that you use.
So
We'll take one more question.
It's a little bit reinventing the wheel, but you can achieve the same thing Kafka is doing just within Akka. And then you have one last moving part. Just can you say a little bit about the deliberation of why still use Kafka and Akka,
Oh, so why use Kafka and Akka together,
versus just Akka and do the message delivery part with Akka?
You could do the message delivery part with Akka. So Kafka is, the reason why I use Kafka is for other reasons. It's because Kafka stores messages on disk. So if things go down, you have a, however much buffer that you store with Kafka, you can. It's more of a. It's a really good way of buffering messages, storing them on disk, and are you talking about instead of using Kafka, you have some service that feeds directly into Akka, or?
Use Akka to do what Kafka is doing. You just have to do a little bit of implementation yourself.
You could do that. You could do that.
Right, so I'm just wondering about the balance of just using Akka and implementing that.
You probably could.
Having like two systems and
Yeah, it probably would be even simpler if you used Akka itself, but I think you would still have to implement what Kafka does for you, which is disk-based, very fast message processing, as a message queue. So you could use Akka for that, but you would have to basically all the stuff that Kafka is really good at, such as writing the disk quickly and all that stuff you would have to do anyway. So Kafka does replicate, yeah. So Kafka basically gives you like disk buffering. I mean, it's like this, right? Let's say you have a huge spike of events, right? On like for us, it would be like the Pope got elected or some event like that, right? So you might not be able to spin up enough new AWS instance or whatever to scale that scope. So Kafka is really nice. It can buffer a whole bunch of messages for you and allow you to absorb that load, right? So you could implement it yourself in Akka, but honestly, Kafka has been one of the easiest to run pieces of software around. It's extremely solid. It pretty much never goes down. So
pretty much Akka's computing Kafka storage.
yeah, but it's starting to blend the line because like now Akka has Akka persistence, which allows you to store stuff on disk. Oh, also, none of Akka persistence wasn't around when we started writing this. That's the other thing, So it's in 2.2. This was like 2.0, 2.1, or so.
So Jake Krebs, the creator of Kafka. Kafka is written in Scala.
Yeah.
We're going to do a meetup in April with him. So I think the difference is Kafka's been in production since 2011.
Yeah.
It's basically a distributed consensus system. If it goes down, right, there is a very rigorous process to define the state, and they tested it in production rigorously, and nothing in Akka stores was tested to this extent, right? Basically, nothing I think in Akka was tested in production at scale and to the extent which Kafka has been for a specific purpose. So it's very fair to use it for essentially guaranteed at least once delivery, right? So it's kind of very initial.
But yeah, I think now it wouldn't be too hard to write a Kafka using Akka, although I would say that the trick is really making it like reliable and all other stuff. So.
Why did you choose Cassandra instead of others? Is it because of its write performance?
Cassandra. That's probably a topic for another talk. But like, really briefly, yeah, Cassandra because we can allows you to easily do immutable it allows you to do to rewrite records extremely well. Effortlessly, like if you were to do the same thing in HDFS, like you can't append to HDFS, you can't like rewrite blocks of the file, right? So, yeah.
I have one more question.
Yeah.
So you have these processing pipelines, right? So it comes into Kafka and then it's going to flow down, right?
Yeah.
So a couple things. So for these actors, are actors capable of message concurrency? Like can they process multiple messages at once in a single actor?
Okay. So the way actors work is that you have one mailbox, and you process one message at a time. So the pattern for concurrency is that you have multiple actors, and you distribute messages amongst them.
So do you have challenges? Because I guess I've done actually a bit of CPU design, and there's a very similar problem to this. When you have a pipeline CPU, and you want to make sure that each stage takes about the same amount of time to execute in order to maximize the throughput, otherwise you get a stall like in the middle. So is there a similar problem to this where if you have one stage, so to speak, of this pipeline that takes a long time to execute and then another one is really slow? Like how does it deal with like message contention or backup or those kinds of problems?
Okay, I think I probably answered that question a little bit. So the way that actors work under the hood is that you have a thread pool. And actors, basically, they can run on any empty thread. And so let's say you look at one thread at a time, you could have actor A running one chunk, and then the next moment you could have actor B, and it gets mixed around. So this works really well when, so actors are designed for the message event processing paradigm where you process small chunks at a time. So it doesn't work as well when one actor takes a long time. That might be the case, for example, if you need to wrap synchronous, like say JDBC or Thrift, or well, in our case, an example is the Cassandra writer. Cassandra uses Thrift, or at least the old Cassandra did, and Thrift is synchronous. So we would need essentially one act. Essentially, it becomes a bunch of actors becomes one actor per thread, and they would take a long time to do the work because it's blocking. So that you would run into some issues like that. Typically, the way we manage that is that any actors that wrap synchronous code, we would spin off in their own thread pool so that we can manage those resources separate from the things that are not blocking.
Like a node-style callback in an actor, right?
There is.
There
so
is.
you can actually spawn a promise with it. So that's one thing. The other is actually going to do, you're going to spawn multiple actors rather than burning one actor with a lot of work. So,
Yeah,
and there's various policies for how to allocate actors and how to share work among them.
The callback is basically a future. So you can send a future to an actor, and an actor can do a reply. And when it does a reply, it will send back a message to the original guy who sent it. And then that future gets completed. And so that would be the kind of callback. Yeah. Yeah. Yeah, no. So cool. So this is really interesting architecture. I'm going to move to the second part of this, which is something I call stackable actor traits. Of course, everyone loves traits in Scala. Like, you can mix in different functionality. So what are actor traits? Well, one common thing that you do when you productionize a system is that you start adding logging. Then you start adding instrumentation, like metrics, tracing code. It starts getting pretty repetitive and ugly. And pretty soon, like, your code, you can't really see the original business logic anymore because there's so much like logging and other stuff wrapping it, right? So stackable traits is a way to work around this and to add standard behavior to actors. So since this is a Scala meetup, we got to have some code, right? So let me see. So if you haven't seen the actor code before, the common pattern in an actor is that an actor is a class, and there's a method called receive. And what is inside the receive is a pattern match. The actors are essentially untyped, so they can get any type of message. So what you do is you do a case with the type of message that you want to act on. So we'll go into this pattern a little bit, where like we're going to wrap the receive method, and that will allow us to add behavior to it, such as logging and tracing and other things like that.
So, sorry, I don't know if I heard you correctly. Did you say you're going to do a bunch of case statements for the type?
Yeah, so let's suppose that your actor has to handle two types of messages, like register and, I don't know, give me another verb. Like, what? Unregister, OK. So you would have a case register and a case unregister. And each one would have some code. So it's a standard Scala pattern match.
So you're going to make that nicer with polymorphism or something?
Sorry, I have a hard time hearing.
So you're going towards like polymorphism to clean that up?
Polymorphism.
It's not so much that.
We can talk later.
Receive is
Yeah.
a partial function. So it's whatever you're going to give it to match, it's going to try to match on that. And if it's not matching, it's like, maybe another one. So you can actually, because it's a partial function, you can start composing it. And by factoring different behaviors into aggregations of partial functions, you get that kind of composition of behaviors. So it's not polymorphism, it's just composition of partial functions.
Thank you. Thank you.
One more thing, would you compare this to AOP with before and after? This looks like a much nicer way of doing it.
I have my opinions on that. If you really want it, I can tell you my opinions on AOP, but.
I don't use it, but this looks much nicer.
I honestly, like personally, I prefer no magic. So I prefer to explicitly know like what is in, what my classes are doing. So I like explicitly calling it out. So we're gonna start with a base trait. By the way, the latest Akka has something that is actually a bit nicer than this. But the way it works is that we're gonna say for your actors, instead of implementing receive, you should implement a wrapped receive method. The reason is because we're going to redirect the receive method to point at this other guy so that we can stack it. if you don't do that, then it gets very tricky. The inheritance gets extremely tricky. So you could do super.receive, but if you end up stacking a lot of stuff, there's a whole bunch of edge cases that don't play very nicely with that. But Akka has something built in now to get around this problem. So I'll give you an example of like two traits. Let's say that you have one which is instruments before and after, and the other one does antes, displays. This simply calls super.receive. And what you do is that you would say extends actor with instrument 1 with instrument 2. And then when you send a message to this actor, you'll see that this gets called in the order that it is mixed in. We'll go into more of these traits later, and how like specific examples. Yeah. Yeah, that was just a really quick example. So this is our Akka stack. We use Spray, which is a pretty high performance HTTP library, which is all like Akka based, with Yammer metrics. 2.x, yeah, kind of fairly standard stuff otherwise. One thing is that for distributed systems, visibility is extremely important, right? So although you guys all know this, we like using Logback because it has a bunch of really nice characteristics, like you can adjust the logging level dynamically at runtime, which is pretty useful for debugging. And we take advantage.
It's a default for Akka.
Sorry?
I think it's the default for Akka.
Well, Akka doesn't. Akka has SLF4J. You can implement any backend you want. The only thing is, like, there is a trick, but it's very hard in Akka. Basically, Akka has immutable configuration. So there's no dynamic way. There's no easy dynamic way to adjust your logging levels because Akka has its own logging level, which is part of the configuration. Although I found out there is a trick around it, apparently. So for example, we would have a trait, a stackable trait that implements Logback style logging, and we would override a receive function. And so before it calls the main receive method, we would do an mdc.put. So what the MDC does is that, so it ensures that when I do my logging, I have a variable that expands out to the actor path. Because one problem with traditional Java logging is that it's thread-based. But in Akka, because your one actor can run on many different threads through its lifetime, like the thread-based logging doesn't help you at all for debugging what actor was running some code. So instead, what we do is that we put the Akka path in an MDC, which is a thread-based thing. And when you do logging, you can see which actor did some work. We also do something nice where like we will automatically print out that an actor started, which is pretty useful for debugging like initialization. Yeah.
Can you speak up?
Or can you repeat the questions?
Sure.
What is the difference between the stackable trade thing and the all else method of partial functions?
Oh, yeah. So he's talking about in Scala, partial functions, you can compose them. The difference is that the stackable traits allows you to wrap code around the receive function. You can execute it before and after. When you stack partial functions, what you're doing is you're running one, and then the results get fed into another one. So it's more of a chain where you do something first and then another, whereas this allows you to wrap it. Like this example doesn't, like this particular example you could probably have done using the partial function composition, but I'll show you another one where you wouldn't be able to do that, which is with performance metrics. So we define a trait that adds 2 metrics for every actor. One is that we want to measure how much time is spent in the receive block. So we want to see what the latency is of a particular actor. Another thing is the frequency, so that these things can be fed into a chart, and you can see how fast different actors are moving, right? So this is something that, for example, you wouldn't be able to do with the partial function approach, is that we're going to wrap a metrics timer around the receive block, and we have a try finally. And basically, this will measure the time of the block, how long it took to do that logic in that block. And when you instrument this way, then you can get like pretty nice charts showing like, these are different actors. And then you can see like how they vary over time, like as a response to load, which is pretty useful for debugging.
Are we pushing back?
OK.
I could ask this after, so you can decide. So I'm coming from a Java background, so I'm just wondering if the stackable traits is kind of like aspect-oriented programming, like where you write.
Well, it's quite different. It's quite different. Yeah. Thank you. So one cool thing that we can do is that we can trace how fast these actors are changing over time, as well as you can trace different nodes, like which ones are doing what. And there's we can see that let me see. For example, like these are different stages in the pipeline. And like there's a spike in the latency at one point. And this kind of corresponds to, like, so you see that there's certain parts of the graph where it's a little bit hard to see, but there's certain stages are falling behind the other stages because the rate is a little bit slower. And for example, like let's say that Cassandra is slowing down. So you could then visibly see that the Cassandra, the rate of messages flow in the Cassandra actor is slowing down. And that corresponds to spikes in latency. Right? So that's how we would use these metrics in production. By default, the mailboxes in Akka are unbounded. This is really interesting because what happens if you keep feeding messages and you don't process them? Then eventually your mailbox will blow up, right? So this is pretty interesting. There's different ways of solving. Like basically, you need a flow control mechanism when you are sending messages back and forth. One way to do it is the cheapest way to do it is or the easiest way is to use bounded mailboxes. What that, is just like a bounded queue in Java. When the mailbox is full, Akka will have a setting where you can define like how long it waits until it's not full. And if it waits the whole timeout and the mailbox is still full, the current implementation of Akka is that this message will go to something called a dead letter mailbox. The old versions, you used to be able to set it so that it blocks forever, but then they got rid of that. Now, there's a major disadvantage to this, is that this only works when your actors are all on one node, because obviously when you do send messages across, then the bounded doesn't. I mean, there's no easy way for node A to check the mailbox size of node B, right? So if you want it to work for distributed systems, and overall, like what the Akka guys recommend is that you work on a real flow control system. For example, you can do a pool-based model where your workers pull work off of the first guy, right? Or you can do push with like Axe. So there's a lot of different patterns you can use. That takes more work, but whereas the bounded mailbox just takes one config change, but like the real flow control system lets you design distributed systems.
So how can you do throttling using that mechanism?
Using which one?
With actors, how can you suggest to do throttling? Basically, not let that overflow happen.
Just reappearing.
Well, I mean, I think it's, yeah, we can talk afterwards. But if everything is local, you can simply use a bounded mailbox. That will slow everything down.
Well, it throws it away.
Eventually, it will get thrown away. So basically, you need. I didn't say that you get like guaranteed message delivery, right? So you still need something that will make sure that messages get delivered. But I think the real answer is that you really want a flow control system that can detect like when you've dropped messages, like when your system is like can't handle anymore and will slow down the source, right? So.
So you can answer this later if you like. So I was just wondering for the real flow control
Yep.
in the distributed case, what does that look like exactly? Do you have multiple actors hitting some like main queue, or do you have multiple?
We can talk later. There's a lot of possible designs. So, yeah. So I'll show you like an example of the flow control system that's working. Is that this is an example of when we first turn on Kafka, and you can see that the actor that is consuming from Kafka like gets a huge spike, and then these are the later actors that are processing the messages after that. And you can see that they start converging. The Kafka one slows down, and this one shoots up, and then they converge, right? So that's the kind of graph you want to see if your flow control system is working. Right. How many people here use Visual VM? It's a pretty useful debugging tool. It's free. It ships with some version. Actually, you can download it from Oracle or whatever. If you use bounded mailboxes, you'll discover that your actors might spend a significant amount of time in this enqueue method, where it's waiting to enqueue messages. So, yeah. Visual VM is really nice for Java, like threaded programming, because you can see like threads doing work. My dream is to have a plugin that allows you to visualize actors instead of threads. That'd be really nice. It offers the typeset console, which is actually free if you run it within SVT. It's not quite the same. I mean, I think it allows you to discover what your actors are and stats about the mailbox for each one. Visual VM is different. It allows you to see like all of the work going on at the same time. So it's a little bit, but yeah, that is a neat tool. We just, you can't use it in production. So, so one thing that is hard about Akka development are stack traces, because you see something like this. You see a few messages and then a whole bunch of Akka to dispatch or JSR166Y or something like that. Basically, you can't see past when you've received the message, because that's a fork join pool and dispatch stuff. And you realize that it'd be really nice if you get an Akka message stack trace, where I can see, you know what, I've gone from this actor to this other actor to that other actor, will like that kind of thing. So we can actually use the stackable trade pattern to solve this problem and get really nice message flows like this. This was a hackathon that we did using d3.js, where you can see kind of a message flow, and the width kind of tells you how many messages have been sent, kind of thing. Pretty neat. So this is not that hard. Basically, we have another trait we call it tracker for tracing Akka. And all this does is we have a partial function called the message ID extractor. And what this is designed to do is, given a message, it will extract out an ID from it. You can define it depending on the semantics of your application. And what this will do is it will send the message ID along with the source and destination actor paths to a collector. And then the collector can build up a graph and create those beautiful flows. So this is another good use of traits. I think this is just some random development practices. I'm not sure I really have that much to say about it. Some good patterns that we use is that, well, what one hint is that, like, unlike traditional classes where you put a bunch of initialization in a constructor and then it fails, you get a stack trace. For Akka, that's more dangerous. If you, the default, so all Akka actors are supervised. So if something happens like an error, then the supervisor can restart the actors, which is a really nice thing. It's a fault tolerance. By default, if you have an error in an Akka actor's constructor, then it will stop it. What you will end up with is an actor that seems to be live, but is actually in a suspended state. It is not doing anything. So my advice is that for any complicated initialization, should put it, have an initialize message and have that work be done in the actor itself so that you can use the normal fault recovery mechanism. So if I put it all together, all the traits that you've seen, this is something that we have. We have, for example, an instrumented actor trait. This mixes in our logging trait, our actor metrics trait, our tracing trait, and you can just add whichever one of these you need, right? And then we have the class extendis, and this is very different from the AOP. Basically, I know exactly what is being instrumented in my code, which I personally prefer, and you get all the other stuff for free without clogging up your business logic. So the next steps, well, this talk, honestly, I gave this talk at the Pacific Northwest Scala conference at the end of last year. And unfortunately, we still haven't open sourced this, but at some point, we are interested in open sourcing it. So talk to me if you're interested. Thank you very much.